Hello everyone, welcome to Wikipedia.com. Wikipedia.com is a YouTube channel for chemistry and related things. Okay, today we will talk about Raman spectroscopy by C.V. Raman. And my name is Ali Sudais. I'm computational chemist, motivational speaker, MD SCA, and ETA instructor. Let's talk about Raman spectroscopy. What Raman spectroscopy is. You know that Raman is actually C.V. Raman is his name, and he is from India. He was from India, and he studied the Raman spectroscopy in detail. Okay, now Raman spectroscopy is actually light scattering technique for studying molecular vibrations. We talked about the IR, so you can go and you can study the IR, or you can watch that video. Then you can understand the basics of the vibrations, and you can also study or watch the types of vibrations, so you can know that how many types of vibrations are there. Change in polarization is necessary. This is necessary for a vibration to be seen in Raman spectrum. Change in polarization, okay, implies change in distribution of electron cloud around vibrating atoms. So change in distribution of electron cloud around the vibrating atoms. Polarization is easier for long bonds than for short bonds. So this is important. For long bonds this is easy, for short bonds this is not easy. IR inactive vibrations are Raman active. Now there are two kind of vibrations, the one vibration which is IR active, the other one which is Raman active. It means that if there is a vibration and that cannot be seen or detected in the IR, so they can be used in the Raman one. Okay, now what are the principles of Raman spectroscopy? Raman spectroscopy is part of the radiation. Part of the radiation is scattered by molecules when the radiation passes through the sample. Okay, so is the part of radiation is scattered. How is it scattered? I'm going to explain this to you in detail, that how can it be. For example, this is a molecule and this is a light, okay, a radiation. As this radiation passes through this sample, this will go, and when this, we call it scattered light. This is the scattered, and this one is called incident, right? Now the difference in this scattered and light, this scattered and this incident, there is no difference, and this radiation and this radiation, these both are same. It means there is no difference. It means nothing happened to the sample, nothing happened, no energy loss, no energy gain. If energy was gained by this sample, it means the light would be of low frequency. It means that there is no difference in this one. So therefore, when you talk about the vibrations or the difference, we talk about the scattered light in here. We talked about the scattered light. Now when we talk about the scattered light, you should understand that actually when we talk about the scattered light, so you should know that the scattering is actually of two types, and those types are, the scattering is of two types. One is called elastic, and the other one is called inelastic. Now what is elastic? Elastic mean that when there is a sample and the light comes, when the light hits this sample, same frequency of radiation is the scattered one. The scattered radiation is of the same frequency as the incident. It means this one and this one, they have the same frequency, so we call it elastic collision. It means that there is no gain and no loss in the energy. So when there is no gain and no loss, we call that one as elastic. So we call no gain and no loss. Okay, so this is called the elastic one. Now, what is the inelastic? The inelastic one is the one in which there is gain of or loss of the energy. For example, there is a, we call it inelastic. For example, there is the sample and a light, incident light comes, it collides with it. But now, when we talked about before that this is the scattered light, and this scattered light has the same frequency as the incident one. But when this time you this scattered light is different from that incident one. When it is different, we call it, it will have less energy or more energy. It means this is of less energy, I mean less frequency, and this is of more energy or more frequency. This type of collision is called inelastic collision. So now you know the elastic and inelastic. In inelastic there is no loss. In the inelastic, sorry, in the elastic there is no gain or loss of the energy, while in the inelastic there is gain or loss of the, yes. Now when you know about these, that there is gain or loss, then you know that, for example, we have this one, this molecule and molecule, okay? A light comes, and when the light is scattered, so we call this the incident light, and the other one, this one, we call it as the scatter light. When they have the same frequency, so this light of the same frequency, we call this Rayleigh. What? Rayleigh. So you see, this is the Rayleigh scattering. So the Rayleigh scattering is actually elastic scattering. It means the molecule, okay, you should know this is the molecule. This is the molecule. So when the molecule is collided with the incident light, and when the light scattered, it has the same frequency, we call it the Rayleigh scattering. It means there is no gain or no loss of the energy. What? No gain or no loss of the energy. This is called the Rayleigh. So now you know about the first one, the types of scattering. The first scattering, that is the Rayleigh scattering. Which one? The Rayleigh scattering, this one. So now we know about this one. There is another one. I'm going to tell you, for example, you have a charged particle, electron, proton, or anything. When you hit this with an incident light, when the light, the scattered light, has a different frequency. It means, for example, I call it nu, and I call it nu bar. It means the nu energy is more than the nu bar. Okay, in such case we call it the Compton effect. Which effect? The Compton effect. It means that there is a charged and then the frequency is different, so we call it the Compton effect. Okay, clear? Now we coming towards back to the words that molecule. We said there is the Rayleigh effect. So we let's check that molecule again, and we take that molecule so you can understand that when there is an incident light and the light goes back, this is of the same frequency. But now what happens? There is this incident light and this scattered light frequency is different. Okay, now you can see the difference, that actually there is the difference, and the difference shows that this light has low frequency, less frequency, and this one has more frequency. Okay, that is what the difference is. Now this happens, this one and this one happens actually once in a million. Like 1 in a million has this different frequency. It means all of them from the molecule, there will be the Rayleigh, but only 1 in million they will show a different frequency. So we're gonna study that, and that frequency, that different frequency, that is called the Raman one. Okay, so that is what the Raman is, and we will study in the Raman spectroscopy about these lights, scattering radiation. Okay, now what is the difference between these two? Like we studied about these two. So what is the difference? Let's talk about these one. For example, let me draw here. Sorry, let me draw here. For example, this is, you can see we call it the relay. The relay, I mean this one. Okay, inelastic. And what happens? Let's take this as a graph, and we took it. There are two possibilities, and those two possibilities are that when you take, you get a peak in here, and this peak is also scattered with a different frequency than this relay, and we also have this one of with a different frequency. Okay, now these are with different frequency, and these different frequency peaks are called, these different frequency peaks are called Raman peaks. And this the actually the scattering is different. There are two kinds of there are two kinds of scattering. One scattering is called the Stokes scattering, and the other one is called the anti-Stokes scattering. Now, which one is the Stokes and which one is the anti-Stokes? Do you know about this? If you know, you can write to me in the comment below. We're going to talk about a few things, and then we coming back to here. Okay, Raman spectroscopy, which is described by CV. He's from India. So in here we observe the vibration. What we study about the vibration, rotation, and low other frequency. It means that rotation. What we study is of low frequency. These are low frequency modes in a system. Raman spectroscopy is commonly used in chemistry to provide a fingerprint for by which molecule can be identified. So it also gives a fingerprint through which you can identify a molecule. And when the radiation passes through the transport, for example, this is the radiation passes, this radiation passes through the sample to the transparent, if this sample is transparent medium, the species present scatter a fraction of the beam in all direction. Okay, it will scatter in a different direction like this. You can see. Okay, Raman scattering is reserved for the same type of the quantities vibration changed association with IR spectra. So the difference in wavelength in between the incident and scattered visible radiation correspond to wavelength in mid-IR region. Okay, so this is how it will now. Now you know about these. That actually, okay, let me just remove these first, and then we can go further. And I can tell you what is this stroke, anti-stroke, and anti-stroke, and relay. These are the three main things. Okay, now let's talk about these one, the relay. So result in elastic collisions between photons and sample molecule energy is same as incident. So we talked about this. For example, this incident light is, it hits this sample, and this scattered light, they have the same frequency. It means this is the Rayleigh scattering, and this is one of the scattering. Now we talk about this, the Stoke and anti-stroke. So the Stoke and anti-stroke, they have the different frequency than the incident. For example, you just hit the sample, and it has less energy than this incident. So there is a lot of difference between these two. When there is a lot of difference between this one and this one, it means this is called Stokes scattering, because it is with less energy than the incident radiation. So it results in spectral lines called Raman lines. Okay, now you understand that the Stokes scattering is actually the Raman scattering. Okay, now the Raman lines result from photon scattering with more energy. So there is another case. For example, just consider this is the sample, and what you do, you just hit it with an incident light, but the frequency is more than this incident light. When it is more than, for example, this is the normal and this is more than this, we call it anti-stoke scattering. What? Anti-stoke scattering. Okay. Now you know that actually we have three kind of scattering. When is Rayleigh, Stokes, and anti-Stokes has less energy than the incident one, and it has the more one. So we talked before that the spectrum is measured with the laser lines as a reference. Hence, the peaks are measured as the shift from the laser line. The peak positions are determined by the vibrational energies associated with the bonds in the molecule of which the sample is composed. Because of this, the spectrum ends up looking very similar to an IR spectrum and is interpreted similarly. Okay, so now you understand that actually peak positions are determined by the vibrational energies. So therefore, we thought that actually the bond in the molecule. So the sample in the sample, both in the Raman and the IR, they are interpreted similarly because of the bonds. So there is a footnote to the principle of mutual uh, okay, let me explain these things in the next slide. Actually, I think it will be more okay. Now, we know that actually the strokes and anti-strokes are due to inelastic. As we said that there are collisions, and the scattering number one is elastic and another one is inelastic. So the elastic is actually Rayleigh. There is no Rayleigh, and the inelastic they are what? They are the Raman. So this process is not quantized. You should know that this is not quantized. Okay, the bands that are emphasized in a Raman spectrum are those that are due to high polarizable bonds, such as those with the pi electrons. With what? With the pi electrons. It means that these Raman spectroscopy actually is based on the pi electrons. Got it? Okay. It means that if there is a pi system, it means there will be Raman spectrum. Okay, radiation measured in near this measured in visible or near IR. Okay, so now you understand. Now you should know that, for example, these are the lines you can know. This is the virtual and this is the ground one. So what happens if when this radiation goes from here to here, but it comes back, it doesn't come to the same position, but it comes to this level, the first level. So we call it is equal to 0 and we call it 1, and this is called the J, or this is called the virtual one. So we call such kind of scattering as stoke, because the stoke, this scattered light is of low frequency and this incident light of high frequency than this one. So this is called the stoke one. Okay, clear this one? Now let's come towards the next one. For example, we extend these lines and we extend these lines. For example, this is the same one and it's here. For example, what happens, that this is the incident light. Okay, it goes from here while it comes back here to the ground one, I mean the lower one. So this one is called anti-stoke. This is anti-stoke because this incident light is of low energy, but this scattered light is of high energy. It means the sample has given some of the energy in here, and it means in here some of the energy has been taken from that light, so therefore there is a difference. It means that if I just draw like this and this, so this one is called Stokes and this one is called anti-Stoke in the spectrum. Okay, so I think now you can understand that what is the difference between Stokes and anti-Stokes. These are very important things. There in the spectrometer is called a Raman spectrometer in the spectroscopy, and we do not need the instrumentation in here for this course. Therefore, for now we will not talk about the instrumentation. Maybe in future I'm gonna explain in very detail the when I have a board lecture, then I can explain that one. Now the basic thing is that what is the difference between Raman and IR? Like this is the Raman, but if we have IR, so what is the difference between these two? So you should remember that in the Raman it is due to the scattering of light by the vibrating molecules. So this is vibrating, sorry, in here, vibrating molecule, the Raman, but the result of absorption of light by vibrating molecule. Okay, so this is what, this is scattering, and Ram IR is absorption. So this is the main difference, that in the Raman the scattering of light happens, but in the IR the absorption of the light happens. So the vibration in a Raman active, if it causes a change in polarizability. So in here the change in polarizability, you should remember this word, polarizability, it means polarizability. Okay, and in the IR vibration, in IR active there is a change in dipole moment. So this is another one, in here polarizability and in here dipole moment. So if you see, when we talk about the dipole moment, we write is nu for that. Okay, how, let me just make it clear, and let me do it with the red one. Oh, sorry. For example, I do like this. In here is Raman, and in here is IR. Okay, I'll try to just write it clear. There in here is scattering of light. What? Scattering of light. But in here is absorption of light. This is the first one, and this is the first very important point. Okay, what about the second point? The second point says, the second point, that actually in here change in polarizability. What? Change in polarizability. But in here there is no change in polarizability, as is the change in dipole moment. Okay, now the third one is the molecule need not possess a permanent dipole moment. Like in the IR, no permanent dipole moment is needed, no permanent nu. But the vibration concerned to the IR should have a permanent dipole moment. I mean a change in dipole moment due to that vibration. So therefore, water can be used as solvent in the Raman, but in IR water cannot be used due to intense absorption peak of Raman. So you can use it water here, yeah, or you can write it H2O, but in IR no H2O. Why H2 not H2O? Because water gives an intense peak in the IR. Okay, in here in the Raman the sample preparation is not very elaborate. It can be in any state, like solid, liquid or gas, whatever that is in the Raman. But in IR there is the problem that the sample preparation is elaborate. Gases sample can rarely be used. Gases can rarely be used. Okay, actually the Raman gives an indication of covalent character in molecule, because I told you there is the pi system, and it explains about the pi system more. But well, in the IR, it indicates of ionic character in the sample, because in here we talk about the permanent dipole moment. So when there is a permanent dipole, it means that there will be IR. Okay, that will be polar dipole moment mean polarity, and the pi system mean no polarity or just a change in polarizability, and there is no permanent dipole. And the IR is comparatively inexpensive. Okay, so it means all these points show that actually it has advantages over the IR, and the advantages are that it can be used
An aqueous solution can be used here because of the water, and we can also the power fewer and much. Okay, see you with a new lecture next time.